back. So last time we covered GPS as we got to GPS as an example of one-way range. We talked a little bit about the atmospheric and relativistic effects that are involved with looking at the different signals. So today we're going to cover a two-way range, and we're going to start working into difference measurements, right? So, thanks. So what that means is that as soon as we're done with these, we're hopping into Fundamentals of Orbit Determination, Chapter 4, because we've made it so far. But for right now, what we're doing is we're giving you examples of different systems. Oh, excuse me, I forgot to mention Doppler. We're doing two-way range Doppler systems, and then finally we'll look at difference measurements before we move on. So one common example of two-way range is satellite laser ranging. And then at the time that the book was written, early 2000s, late 90s, NASA had this concept of where they could deploy automated satellite laser ranging stations throughout the world, right? And so what the idea was that you could have these laser ranging stations, almost the same idea as SatNOGs, right? Like I queue up an observation, it hits the laser, comes back, but the things that we obviously have to consider with that are not only the fact that as the laser traverses through the atmosphere, it's going to disperse, right? And so I have to have specially designed reflectors on that satellite, or at least the satellite has to be able to reflect that beam back to the source, right? So you get those automated satellite laser ranging stations, you get satellite-borne altimeters out of the same concept where you just want the return to come back to the satellite, and based on the round trip time and the estimate that we walked through in that example a few lectures back, you can figure out the residual between them and then do some extra processing in order to try and reduce your error a little bit. But at the same time, it's just, with more observations you reduce your error. But the idea being that you can take the round trip time and the estimated time and figure out about where you're at for your altitude, or about what the range is between the ground station that pinged you and the satellite. If it's an altimeter, it's the satellite pinging the ground, right? So, fun fact, you do have to use the DoD clearinghouse if you're going to fire a laser in space. Might hit things that aren't there, right? Topex Poseidon, so I'll show you guys in the book, there's going to be there should be a better picture of it right here, but that is a specially designed reflector, right? Topex Poseidon had it installed. Excuse me, sorry, that's the ISAT SLR. Topex Poseidon has one as well, but the idea being that it's the specially designed reflectors in order to reflect the dispersed beam back to the source, right? Why it mentions Topex Poseidon here is specifically for the altimeter, because there's I think it was USNO, but long story short, so the United States put an altimeter on there, and the French put an altimeter on there. And the French one only uses one frequency, so they can't correct for the ionosphere dispersion or the effect on the radio wave, right? They're using gigahertz, like 13.6 gigahertz or something like that. But the French can't correct for that dispersion. However, the United States one can, because it uses two frequencies. And so you can cancel out that error in your signal received. TDRS is another one, but TDRS is a long way of doing it. TDRS is let's see if I can get this right, transmitted data relay something system. Let me pull up the book. It is NASA Tracking and Data Relay Satellite System. And so they have at least 3 geostationary satellites, right? And so these suckers have a pretty broad view of the Earth. A TDRS time is always maxed out because what you do is you're not always going to be over ground station, especially if you're in LEO, right? But you are always going to be in view of a geostationary satellite. So I can ping TDRS, and TDRS can send the information I sent to it back down to a ground station, right? So that's the concept with TDRS. There are multiple on orbit, but the other idea with it is, let's say it's, in one way, it's a two-way range, right? Because if I send a signal from a ground station to TDRS, right? So I'd have to estimate where TDRS is. I'd have to, have some information about the ground station. So now we've done one way, right? I go to the satellite. I come back through that same channel. That's two-way ranging, right? It's a long way of doing it. Your estimates of TDRS's state are tied up into the errors in that as well. But it's another way to do two-way ranging. Let's see. And especially if you're already getting, if you're already getting data from it, why not, right? So, Doppler systems. So, very first ones to employ Doppler, the Navy. Navy's always doing good things with satellites. Navy actually was a lot more advanced than the Army, despite their initial success. The Navy put up the navigation satellites to start off, right? So Navy navigation satellite system, I think, but it's NNS. No, it's NNS. All right. So the traditional roles here, something to take in mind, or a little bit of history. The Navy actually is technically the ones that run the tracking stations. Up until the Space Fence, which the Air Force put out a RFP for. So the Space Fence is a big old radar station that Lockheed Martin built out on Guam. And it supposedly can track, get an estimate of the majority of satellites overhead. Does well, then there'll be, more stations to follow so that you can get the rest of the Earth. But it can track a majority of the stuff in orbit and can get down to the centimeter level, which is unprecedented because right now we can only get softball size with the tracking systems that we have. But Navy runs the tracking system, and the Air Force runs the catalog and the system and the estimates and provides the officers. But the Navy has been the one that's traditionally needed it up until modern warfare, right? Or, well, not modern warfare, but in the last 20 years. Because the Navy had nuclear submarines everywhere, right? And so that's why they put the navigation service up, was so that you could talk to your nuclear submarines and they could track their position by using the satellite information, right? Let's see. Yep. Yeah, operations of the Navy navigation satellite system ceased with GPS in the 90s. But yeah, so they broadcast two frequencies, 150 megahertz and 400 megahertz. And so as they're transmitting these, you can provide the ionosphere correction, and you're still going to get your Doppler, so you can figure out where you are, you can figure out what the satellite is, right? Like, so long as you have a good estimate of the satellite, then you can know where you are, right? So it's a one-way Doppler, right? Because you're looking to receive it. Let's see. GPS carrier phase is another form of Doppler. So two ways to do Doppler, right? If you want to predict where your satellites are. Satellite passes overhead, transmitter beacon, continually transmitting at some certain interval, right? And ground station hears it, takes in the apparent frequency, figures out the range based on some knowledge that you have, maybe from the TLE or whatever, right? Flip side of that is what if I put a bunch of different transmitter beacons all over the Earth, and the satellite listens to those as it passes overhead? It's called Doris, and the French did it because it's cheaper. So that's another way of doing it, where you have a transmitter beacon, because you're still going to get a Doppler shift as you're passing over it, right? The parent frequency is going to change. So same concept, just now we're going to put them on the Earth and let the satellite figure it out, because we've highly determined these locations, and these are a lot cheaper to do than a bunch of satellites. So, let's see. So that's Doppler, GPS in action, which, so, let's see. So let's talk about difference measurements for a second. So the whole point of difference measurements is to try and reduce or take out the error in some way, right? So if I've got two pseudo-range measurements from two different receivers, maybe I can difference them, and I'm removing, maybe they both have the same receiver, right? So then I'm looking at, okay, well, you know, what's my constant bias in this, right? Or maybe I take two different receivers, because that wouldn't necessarily cancel out your constant bias, but I take two different receivers, I subtract them, I see some linear term that's constant in one receiver. Okay, now I've identified a bias that's present in that one receiver, right? So that's what we're trying to get at with difference measurements, and this is why it leads into fundamentals of orbit determination, basically the solution. Okay, I've got many, many observations. How do I improve my estimate of my satellite, right? Because difference measurements is the same concept where we're just trying to, or it's the lead-up concept where we're trying to remove some error that we either know about or we expect to be in there or that we don't know about and we're trying to find, right? So for GPS, you can take a single difference. So let's take selective ability first for a second. So do you remember what selective ability when we talked about GPS a little while ago? No? Okay. So selective ability is essentially when they dither the clock, right? The people that know how to do orbit determination eventually got a hold of somebody and said, what the hell are you doing? Get rid of it. Because it actually gave you a more precise measurement when they dithered it. So they would mess with the clock, right? And by messing with the clock, they would, at random, give you worse results, right? So the trend, though, was the same because of the way that they did it. And so if we take two pseudo-range measurements, we take a single difference, so we take one, so it's literally just one minus the other, right? And just recorded by two different receivers, or maybe we have measurements recorded by one receiver and two different satellites. Either way, we can form the residual by just taking the observed minus the computed, right? And so for each one, okay? So what we should find is, so in big terms, we're taking each residual and we're subtracting them to find the trend, right? So by doing that, selective availability provides some high frequency variations into the signal in order to mess with the clock. So since it's satellite dependent, if we have two different satellites and one receiver, we might see it a little bit different, but we'll still see the same trend. If it's two receivers and one satellite, we're really going to see the trend where, for instance, here I'll show you, should be here as well, but so you guys can get a closer look. The magnitudes clearly are different, right, for our residual, but it's the same trend. And so we can actually improve our estimate because we've taken out selective availability's effect on our on our determination or on the signal received. Yeah. So that's just one example of difference measurements where we either take two receivers, we take one receiver, two different satellites, but we take residuals of two different measurements and subtract them to try and find the trends or find the error, right? And so while the magnitudes that we showed are different, it's still showing a linear trend so that we can correct for that selective availability provided some other information other than GPS, right? So, because now I know exactly what it's doing, now I can go correct for it, right? I can say, nope, screw you, I've taken you out of my signal received, out of my pseudo range, which it's pseudo range, so we have to know the true range anyways, but if I have some true range information, maybe I have a satellite laser ranging, maybe I'm, maybe I have some other system that's not listening to the GPS signal, right? Or I'm measuring my range. Done. I can correct for it. I can get a better estimate of where I'm at. Difference altimeter data is going to be the same concept. And then finally satellite position and angles. Oh, so know your history, mini-track system. So the mini-track system was originally employed, so we're going back to observations for a second. So the mini-track system, Navy, right, places all these stations around the world, but what it does is it only measures through angles, okay? And provided, your angles and the change in time, you can actually develop the orbit prediction. Have you guys worked through that at all? That'd be like closing in on Lambert Solver or Gibbs, actually. Have you done those? Yeah. You guys haven't taken an orbital mechanics class, which, okay. All right. So you will get to that. That will probably be one of the midway through assignments that you do, is taking 2 or 3 angles and the time difference between them, and then trying to develop an orbit out of it. So, any questions? All right. Thanks for having me. I think we're done for today with Lecture 12, and we're going to follow up with fundamentals of orbit determination. So, linear least squares and Kalman filters and the whole like. So, all right, cool. Let's call it a day.
Is that chapter 3?
4. We were doing 3. Yes.
Yeah. Okay.